Hello, it's Keith here, and this is lesson 41 of the platform-specific series of my 68000 assembly programming tutorials. And we're back on the ATARI-ST, and we're back looking at sound again. Now, what are we doing today? Well, we're going to be looking at ChibiSound Pro. You may remember, or you may not, that the original ChibiSound was designed for simple beeps. This was designed for your Atari Space Invaders type games, very simple sound effects. But ChibiSound Pro, while not really very professional, it's a bit of a joke title, it does give a lot of extra functionality. It's designed for multiple channels, a wide range of volumes, a wide range of pitches, noise effects as before, and it's intended for potentially music. And I've written my own music software called Chibi Tracks and a tracker called Chibi Tracker Pro, and that combined with this ChibiSound Pro driver make a system where we can play a music file on multiple systems in the same binary music file without even re-exporting it. So that's what this is designed for. Now, ChibiSound Pro provides three things. It provides a channel number with noise on and off, it provides a volume, and it provides a pitch. And the volume is now 0 to 255 and the pitch is 16 bits, whereas before it was just 5 bits. I think it was 6 bits before, wasn't it? So we've upgraded a lot from the original ChibiSound, so maybe we deserve that Pro moniker after all. Now, the D3 byte will have the bits 0 to 6 as the channel number, so 0 to 127, and the top bit is noise on and off. Now, why are we storing a byte in D3? Well, that's because this is all converted from Z80 code, basically. D6 is the byte volume, so this will be 0 to 255, with 0 being channel off and 255 being the loudest. And D2 is a 16-bit value, and that will be the pitch, with the lowest numbers being the lowest pitches and the highest numbers being the highest pitches. And that's what the ChibiSound Pro driver is designed to provide for us, to allow us to do music. Now, one thing it doesn't do is it doesn't guarantee the range of pitches, so the value 32768 will not sound the same on every system. What we have is a lookup table for the notes in the octave to solve that. Now, I don't know if you remember, you possibly don't, but basically to control the AY sound chip on the ATARI-ST, we have two ports we need to use. The port FF8800 is the port to select a register, an AY sound register that is, and then we send a byte to FF8802, and that is the new value for that register. And you can see we've got a wide variety of registers here to control our channels. Now, there are 3 channels on the AY sound chip, and there's 2 bytes that define the low and high pitch of the channels, and you can see we have a 12-bit pitch there, so there's a pair for each channel, channel A, B and C as they're marked here. We have a noise generator frequency, which is for all of the channels. We have a mixer and 3 bits, 3 relating to the tone and 3 relating to the noise, and these turn the channels on. Now, a value of 1 actually means the channel's off, and a value of 0 means the channel is on. We then have the volume bits here, the 4 volume bits that are defined for each of the channels. We also have envelope options, but I'm not using envelopes within the functionality of the Chibi Tracker Pro. It would have been too hard to port that to systems that didn't have AY sound chips, so that is not included within the functionality. But we have some registers for that functionality as well, which, as I say, you will not see in today's example. So let's go over and let's actually see what today's example can do. Well, the example we're going to be looking at today is the Chibi Tracks test and also the ChibiSound Pro test. Mostly the ChibiSound Pro test, the Chibi Tracks I'm still doing some finishing work on. But basically, the ChibiSound Pro test is just a very simple test routine to allow me to debug the actual code. So let's just start up our emulator here. Okay, so this is my testing routine, and basically if I use the joystick up and down here, I can change the pitch, and if I press the fire button, I can turn the noise on and off. And this is designed for me to test the driver and also to set the frequencies. As I say, there is a lookup table of valid frequencies for the notes of the octave, and I used a frequency analyzer along with this to select the correct values for those frequencies. That is usually the best way I find of doing it. It's the easiest way for me. Sometimes if the mathematics is very easy, sometimes I do it mathematically in a calculator or spreadsheet, but in this case I did it using a frequency analyzer. Now, that is just the simple test program, but what is far more interesting is the final result, which is the Chibi Tracks multi-platform, multi-CPU music player. So if we just fire this example up here. So what do we have here? Well, this is the music that was originally in the Chibi Akamas game, the first Chibi Akamas game. Now, this music was written with Arcus Tracker, the Arcus Tracker software, which is far superior to mine, I can't lie, but that is not multi-platform. And so what I did is I converted the Arcus Tracker file to the Chibi Tracks format, and then I exported the Chibi Tracks file into the binary file that the player that we can see here is playing. So this is a file that was originally written on the far superior Arcos tracker, but my tracking software, my music player, is capable of playing, roughly the same song. So, but the most important thing to take away from today's example is that the binary file that you're hearing played there was not written for this system. It was written for an Amstrad CPC, and it doesn't just play on AY systems. The same binary file can be played on any system that ChibiSound Pro is written for, which is pretty much all of them in my tutorial series. So I think this is an interesting little project. Hopefully you agree. So we're going to take a look today at the example code, and we're going to see what is actually involved in the driver for the AY on the ATARI-ST. Now, the first thing we need to discuss is how we're dealing with the channels. Now, this system has a total of 3 channels, which are numbered 0, 1 and 2 here. Now, the problem is we could be given a channel number from 0 to 127 in theory, and so we need some way of mapping them accordingly. And so what I've done is I've created a lookup table for the channels, and you can see we're prioritizing the first channel because the first channel is always the most important in Chibi tracks, and then later channels maybe have something bad done to them, like maybe repeated or maybe ignored. And so I've created this lookup table for up to 8 channels here, mapping them to various bytes here, and then we've got a channel mask here, and this is the bits for the mixer byte. The mixer register 7 needs a sequence of bits relating to the noise and the tone, and so the bits for channel 0, 1 and 2, as we may be numbering them there, are shown there. Now what we've also got is a cache, an AY cache, and this is to store the previous values that were sent to the registers. The reason I've done this is twofold. Firstly, we might need to get the previous value for the mixer specifically, but it was also to reduce the number of writes to the AY hardware, just in case that was causing distortion of any kind on some of the systems. So I'm using that cache to minimize the number of writes to the underlying hardware. Now, when we want to work with the hardware, we've got 2 functions to help us out. We've got the do channel mask function, which will take the bits in D6, and this is mostly the channel number. As I say, the top bit is actually the noise status, but we're taking the bottom 2 bits to get a value from 0 to 4. We're then reading in from the lookup table to get the channel mask here. We're moving that into D2, and we're also moving that into D0 here, and that is the mask for the mixer settings that we might want to change. What we're also doing is we're loading the effective address of the previous value of the mixer into A1 here, and we may use that later. We'll see that later on. So that's how we're getting the correct mask for the bits that we in our mixer. We've also got this more frequently used AY read write function here. Now this is going to actually write the registers to the hardware, but first what it's doing here is it's checking the matching register in the cache and seeing if the register has actually changed, and if it's not doing anything. If it has changed, it's updating the cache, and then it's writing the register number to port FF8800 and then the new value to FF8802. So that is effectively setting the register D0 to the value D1 here when we call this, and we're going to see this throughout our program. Now, at the start of our routine, what we're doing here is we're setting up the AY cache here with an initial value which is all of the channels are silent. So that's the starting position, so that when anything tries to sound, it will actually do so, because otherwise it might check the cache and see that the cache is currently set and think that nothing needs doing. So that's what we're doing there. Now, when we want to actually set the channels, any one of the channels, we would run the ChibiSound Pro set routine. This will take the values in D3, D6 and D2, and it will set the volume, the channel number and the pitch. So these are going to be used to actually set one of the channels to a new set of values. Now the first thing we're doing here is we are getting the noise bit from D6, because remember D6 firstly sets the channel number, but the top bit also handles the noise state. So we are backing up the noise state into D4 effectively here. Then what we're doing is we're taking the channel number, the bottom 3 bits, and we're effectively getting a value 0 to 7 here of the channel number, converting from the potential 0 to 127, and we're reading in an actual channel number from the channel map here, and then we're ORing back in the top noise bit so that D6 still has its functionality. So we've converted 0 to 127 effectively to 0 to 2 here, which is the number of channels we really have. So that's mapping effectively sort of virtual channels there. That's what we're doing. Now what we're doing next here is we're testing D3. D3 is the volume. If it's 0, then the channel is silent, and so if the channel is silent, then what we're basically going to do is we're going to effectively set the bits to 1 in the mixer of this channel number. And so what we're doing here is we're masking the bits that we will need of the mixer byte. Now we're getting that with the do channel mask function here. So that is basically keeping the bits of this channel that we want. And then what we're doing here is we're getting the current state of the mixer byte here, and then we're ORing in the bits for this channel. Now setting the channel's bits to 1 will silence the channel, so we're effectively silencing the noise and the tone for this channel. We're then selecting that we want to change register 7 here by moving that into D0. D1 is the new value of the register, so we're then running AY reg write, and it's a jump here. So we will actually never return because we've just silenced the channel. That's all we need to do because the channel's off. Okay, now what about if the channel isn't off? Well, the first thing we're going to do is we're going to set the pitch. Now the pitch on this system is a 12-bit value. So what we're going to do here is we're basically going to get the range of values that we need. So what we're doing first here is we're taking the pitch in D2 and we're flipping the bits, because the way that this routine works, we want the low values to be low pitches and the high values to be high pitches, and so we are actually having to convert that, because on the AY sound chip it's the other way around, which isn't what I would prefer. So we're doing that there, and then what we're doing here with this bit shift 4 bits to the right is we're ditching 4 of the bits, because our value in D2 is a 16-bit value, but this system only uses a 12-bit value, so we're losing 4 of the bits there. Now what we're going to do next is we're going to effectively work out what register numbers we need to work with, and that's going to relate to our channel number. We could have a channel number from 0 to 2, and we either want to use 0 and 1 for the low and high parts, or we want to use 2 and 3 or 4 and 5 for the 2-byte registers for each of the 3 channels. So we're basically taking the bottom 3 bits of D0 here and we're shifting to the left by 1 bit. Now actually we could have just taken 2 because we've actually converted this to a 0 to 2 value anyway, but basically this is getting us the base of 0, 2 or 4 for the low part of the 2-tone registers that we will want to set. So that's what we've done there. Then what we're doing here is we're taking D2 and we're basically just keeping the low part of that, and then we are running AY reg write to set the L part of the matching channel. So that's set the low pitch part. Now we're then adding 1 to our register number, so we're going to now work on the high part, so 1, 3 or 5 here. And then we are doing a bit shift of D1 after we've moved D2 into D1, and then we're effectively just keeping the bottom 4 bits of that. That is going to be our high part of the register, and that's because the high part only takes 4 bits. So that has set the entire tone now. Now what we're going to do next is we're going to see if we actually are using the noise, and that is defined by the top bit of D6. So if noise is off, we're going to skip down, but if noise is on, then we're going to need to set 2 bits in our mixer. So what we're doing here is we are getting the channel mask of the mixer, and we're keeping the bits that relate to the channels, and then we're flipping those bits. Now this is effectively setting the bits in D2 so that the channel that we want to change has a 0 in those bits, and the channels that we don't want to change have a 1. And then what we're doing here is we're doing an AND with the current state of the channel, and that is effectively setting the bits for the noise and the tone to a 0. Now when the mixer bits are set to 0, the N and T there, that will turn on that function, and so that is effectively turning the noise and the tone on for the channel that we're working on. That's what we're doing there when we set that register 7 with this command here. Okay, so that's what we've done there. Now we actually backed up D2 here, and the reason we did that is we actually wanted to use D2 for something else. Now the D2 is the pitch, and we've set the pitch with the tone, but the noise channels take a different kind of pitch. These take a frequency that is just 5 bits, and so what we're doing here is we're doing another bit shift and effectively keeping only the top 5 bits of the original 16-bit value there, and we're using that as our noise frequency, and so that's being used for our drums and our sort of cymbal effects there basically. And so we're setting register 6, and register 6 is our so-called noise generator, and it's 5-bit value there. So that has done our noise. Now in that case there's still a little bit more we will need to do. We'll need to jump back and we'll need to set our volume. But what we will do next is we'll have the routine for if the noise is off. Now the routine is a little bit more complicated. We're getting the mask for the channel that we're working on. Now what we're doing here is we're basically keeping the 3 bits there, those relate to the noise. Now we want to set the noise channels bit to 1 to turn the noise off, but we want to set the tone channel bit to 0 to turn it on, and so we're knotting those bits there, So basically that will set the bit relating to this channel to a 0 and all of the other bits to a 1. And then what we're doing here is we're getting the current state of the channel, of the mixer, into D0. We're then ANDing with D2. That is effectively zeroing the bit relating to the tone channel for the current channel. We're then ORing with D5, which we prepared up here, which is effectively setting the noise bit to 1, and that is setting those bits so that when we set the mixer, that will turn the tone on and the noise off. And we're then moving that into D1 because that's what we need for our AY Red Right function, and we're setting the mixer accordingly. And so that is setting the noise and the tone bits here. Now I think I could have actually maybe I could have probably neatened up these registers a little bit, used D1 more quickly up here rather than shifting around a bit. The reason for this is this was partially machine converted from the original Z80 code. I've done a little bit of optimization, but I guess it still needs a little bit more work potentially. So anyway, that's how we're setting the noise or the tone on there. The final thing we're doing here is we're setting the volume. And so how do we do that? Well, we've been passed a full byte in D3, but we only need 4 bits for this system. The AY only takes a 4-bit volume. And so what we're doing here is we're shifting 4 bits to the right. So we're only keeping the top 4 bits there, top nibble. We're then basically loading in the channel number here into D0. We're masking out the bottom 2 bits here just to make sure we've got a valid channel number. We're adding 8 to the channel number. The reason for that is that the volumes start from channel 8 and there's 1 per channel. And so that's what we're effectively calculating here in D0. We are calculating the first register that we need to change, the only register we need to change for the volume of this system. And we've got our correct volume in D1. And so we just finally run AY Red Right to set that channel's volume to the correct 4-bit number there, and that finishes everything we need to do to set our channel. So basically all we need to do is repeatedly run this for as many channel changes as we need to make for each tick of our music software, and that will do the job. Now ChibiSound Pro Update, you'll see, does nothing here. That's for systems like the ZX Spectrum, the old beeper that needed processing power every tick to keep the sound playing. So on this system it just returns. And then the final thing to see here is the so-called Chibi Octave, which is a lookup table. And this is so that we can read in the various notes of the octave here. And we've got the octaves going down and the notes going across. And these are the pure tones. If we want a sharp or flat, we simply add 2 values together and divide them by 2. And what we need to do is we need to set D2 to one of those values. And that will correctly set the sound to the correct pitch for those notes. Hopefully anyway, as long as I've got my table correct, which it actually wasn't the other day. There were some mistakes in it, so I had to correct them. Anyway, that's all we're going to be looking at today. If you like what you've seen, please like and subscribe. That always helps me out. If you want to support this content, you can of course buy my books. And if you're interested in seeing more work done on this concept of the music software, please consider backing me on Patreon. The reason being that I'm having to do things like write the music software in Windows. That's taking an awful lot of my time, and when I'm writing music software, I'm not writing tutorial videos and I'm not writing books. So it's effectively time that's just disappearing and doesn't produce any revenue for me in any other way other than Patreon backing. So please consider doing that if this is something you want to see me pursue further, because it's not really something I need for myself. Anyway, I hope you've enjoyed what you've seen. Thanks for watching and goodbye.